Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is the inverses of matrices. So let's get started. So let me quickly tell you what an inverse is. In fact, what we are going to do in this lecture, maybe you don't need to watch this video. So if A is an n by n matrix, then the inverse of A, some other, if it exists, it might or may not exist, if is another matrix, another n by n matrix, B, with the property that if you multiply the two matrices together, if you find AB and BA, you get the identity matrix. If you don't know what multiply matrices or what the identity matrix is, watch my previous videos on the subject. This inverse of A, this matrix B that maybe we find that when you multiply by A, you get the identity matrix, is denoted by A inverse. We read that as with A with a superscript -1. We read that as A inverse. Now, if a matrix has an inverse, it may or may not, again, then it's invertible. If it doesn't have an inverse, then it's called singular or not invertible or non-invertible matrix. So inverses are only for square matrices. They're only defined for square matrices. For non-square matrices, we have something called a left inverse and a right inverse, but we will not get into that in this lecture. Some matrices are invertible, others are singular. One of the things we will prove in this lecture is that if A is invertible, then that A inverse is unique. There's only one matrix that plays this role of A inverse, and that's why we can call it the inverse of A. So that's one thing we will prove. We'll also prove that the product of two invertible matrices is invertible. If you like invertible matrices and you have a few of them, by multiplying them together, you can find other ones. Other things that are true, but we will not prove here, one of them is that you actually don't, for square matrices, you don't actually need to check both AB and BA to see if A and B are inverses of each other. If one of them is identity, the other one will be identity also. That will be a part of a later lecture to prove that. Another thing that we will also not discuss in this lecture, but we will discuss in future videos, is that how you decide if a matrix and 10 by 10 matrix is invertible, and how do you find inverses? That will be subject of several lectures. In one particular lecture, we will give the algorithm for finding inverses and prove why that it works. I will actually mention it here, but I will prove it that it works in a future lecture. But so now to get to those, I first want to motivate the definition of a matrix inverse and why we would want to do that. So let's start with a system of linear equations. So here's a system of 3 equations and 4 unknowns. It's a system, and we have done this before. We can write the coefficients as the coefficient matrix. We can write the unknowns as a vector called the vector of unknowns, and we can write the right-hand side entries, the 3, 5, and 7, as another vector. If we do that, then we can ask to consider the matrix equation AX equals B and ask about that. What does that mean? A times X equals B. A is a 3 by 4 matrix, X is a 4 by 1 column vector of unknowns, and B is a 3 by 1 column vector of the right-hand side entries. So what does AX equals B mean? Well, let's see what it says. Well, what is AX? AX means takes the matrix X and multiply it by the column vector X. And how do we multiply that? Well, we take the rows and find the dot product with the columns, and each one of those will give us one entry of AX. Again, subject of a previous video is matrix multiplication. So solving AX equals B is the same as finding AX, putting it equal to B, and seeing what X, Y, and Z, and W will make AX equal to B. X is the unknown, the capital X here. And AX here will be 3x minus 2y plus 5x minus 8w. And for the first entry, the second one will be minus 2x plus 3y minus 2z plus w. If you take the dot product of the second row and that column vector, that's what you get. And the last one will be 15x minus y plus z minus 2w. If we want this to be equal to 3, 5, 7, that means we want this first entry to be 3, that second entry to be 5, that third entry to be 7. So we want to find little x, y, z, and w that make all those 3 things work. That's the same as solving the original system. So in other words, we have encapsulated that whole system into this nice little matrix equation AX equals B. So the matrix equation AX equals B represents a system of linear equations. Even though it's very compact and it looks AX equals B, then it is a system of linear equations. The coefficient matrix is A, vector of unknowns is X, and the right-hand side vector is B. And vice versa. If you have a system of linear equations, as we just showed, you can translate it to something called AX equals B. If A is M by N, M rows and N columns, then we have M equations and N unknowns. Now, the question is that, can we solve AX equals B the same way we could solve 7x equals 47? Actually, for this A, we can't quite do this, but well, we can discuss whether or not we can do this or not. So the question is that, how do we solve 7x equals 47? Familiar to you from middle school. So we would say 7x equals 47. Well, that means that x equals 47 sevenths. But let's unpack that. How did we get from the left to the right? How did we isolate x? Well, what we said is that, well, if 7x and 47 are two things that are equal, then if we multiply them by 1/7, they will still be equal. So 1/7 and 7x is the same as 1/7 of 47, because 7x is the same as 47 supposedly. And then we said, well, 1/7 times 7 is 1, and so on the left hand side we have now isolated x, and on the right hand side we have 47 sevenths. Okay, now where did the 1/7 come from? Why did we multiply both sides by 1/7? Well, we multiplied both sides by 1/7 because that 1/7, when multiplied by 7, gives 1. And that was the crucial thing. 1/7 was the inverse of 7, was the number that if you multiplied by 7, you got 1. But why did we want 1? The reason we wanted 1 was because it was the number that when you multiply by x, you get x, and that's what allows you to isolate x. So we want to do the same thing for matrices. First of all, what plays the role of 1, and what plays the role of 1 over A? So if you have AX equals B, you may want to do that. So B is an N by M matrix. And first we want to talk about the 1. What plays the role of 1? The identity matrix, N by N identity matrix, that's the matrix that's N by N, that has 1s down the main diagonal and 0s everywhere else. Then that matrix plays the role of 1, meaning that if just like 1, if you multiply 1 by x, you get x. If you multiply this IN by any N by M matrix, you get that matrix back again. And the proof of the pudding is the eating, just multiply it. If you multiply the identity matrix, which again is an N by N matrix with 1s down the diagonal and 0s everywhere else, by any matrix that has N rows and M columns, you take the rows of identity, like for example, take the second row, and when you multiply, that 0, 1, 0, 0 tilts, and then as you're multiplying it by these columns, will pick up the second entry. So when you multiply that second row by that, you just get the second row. When you multiply the first row, you get the first row, and so on. And what you end up with is the matrix back again. So this identity matrix plays the role of 1. Now, if I want to be able to multiply the identity on the other side, I will have to multiply B, which is an N by M matrix, not by IN, not by N by N identity, but by M by M identity. So if I want a 1 that works both sides, then my matrix has to be a square matrix. The system that I had, the coefficient matrix was not square. We still could do something like we're going to talk about, but not with a full inverse, but with just a one-sided inverse. But I'm not going to talk about that. So to make sure that we have a 1 that works on both sides, we will limit ourselves up to square matrices in this talk. So what about inverses? What about the thing that we said, what is the, like 1/7, 1 over A? By the way, we never ever write 1 over a matrix. We only use this inverse notation. So if A is an N by N matrix, then I'm repeating the definition of an inverse. An N by N matrix B with the property that if you multiply the two either way, you get the identity matrix, is called the inverse of A. And we write B equals A inverse. So your friend is an N by N matrix. You look around and you find this other matrix B, that if you multiply A times B, you get identity, and B times A is identity. And then from then on, you can call B B if you like. That was the B's original name. But because now you know that it's the inverse of A, you can also call it A inverse. So A inverse is reserved for a matrix that when you multiply by A, you get identity. A square matrix may or may not have an inverse. If it has an inverse, it's called invertible. If not, it's called non-invertible or singular. So a singular matrix is one that does not have an inverse. So for example, here's the matrix A, 3 by 3. The first row is 3, 1, 0. The second one is 2, 1, 0. And the third one is 0, 0, 1. What is its inverse? I'm not going to tell you how to find its inverse, but if a matrix walks through the door, B, I mean, I will tell you how to find the inverse in a future lecture. But if you make, for now, if a matrix walks through the door and says, "Oh, I'm the inverse of A," it's easy to check. You just multiply the two matrices. And in this case, if you multiply A by B, so how do you multiply two matrices? Watch my video on multiplying matrices, but you take rows of A and find the dot product with the column. So if you want the one entry of AB, you take the first row of A, dotted with the first column of B. So you get 3 times 1, that's 3. 1 times minus 2 is minus 2. 0 times 0 is 0. 3 minus 2 is 1. You get a 1 on the 1, 1 entry. And if you do that for all of them, you will see that you get identity. And therefore, this B is A inverse. Now, you might actually say, like, and A is B inverse, by the way. If B is A inverse, A is B inverse. You might say, how did we find A inverse? And I'm going to tell you without any reasoning right now, although in a future lecture, a couple of lectures down the line, I will explain exactly why this method works and look under the hood and see why it exactly works. But again, as a spoiler, this is what you do. You take the matrix A and you augment it by a full identity matrix. So here's the matrix A again, but you write here the identity, the 3 by 3 identity matrix next to it. Then you do elementary row operations. How? On the whole matrix. This new matrix is 3 rows, but 6 columns. You do elementary row operations on the whole matrix, but you only focus on A and try to get A to become identity. And by the time A becomes identity, if it does, then the other side becomes the inverse. So here, that was A and this was identity. We ended up with identity and then A inverse. So that method works if the matrix is invertible. If it's not invertible, you will not be able to get identity at the reduced row echelon form of your matrix. And why all of that is true will be subject of a future lecture. Now, here's another example, the matrix 1, 3, 3, 9, and is it invertible or not? Now, you could do what I just said, but we don't know why that works. I want to actually convince you that this matrix is not invertible, that this is a singular matrix, and I want to do it in a roundabout way, just as a sort of a proof of concept, sort of getting used to some of these matrix manipulations. So this is what I'm going to say. I'm going to say, look at this matrix D, minus 3, 6, the first row, 1, minus 2, its second row. This matrix I pulled out of a hat. You don't know where it came from. But I picked this matrix D, and then I'm going to ask you, what is A times D? Well, A times D is a 2 by 2 matrix because A is 2 by 2 and D is 2 by 2. What is the 1, 1 entry? Well, you have to take the first row times the first column. First row of A times the first column of D. 1 times minus 3 is minus 3, plus 3 times 1, we're finding the dot product, will be 0. So that first entry, that 1, 1 entry is 0. What about the 1, 2 entry, the entry in row 1, column 2? So again, take the first row of A and dot it with the second column of B. 1 times 6 is 6. 3 times minus 2 is minus 6. We get another 0. And if you repeat that for the second row of A, you get again 0 and 0. And so A times D is 0. Okay. So what? Well, and I'm going to denote that so that I don't have to write it over and over again as the 2 by 2 0 matrix. Okay. Now, what I'm going to say, I'm going to do a proof by contradiction. I'm going to say, well, assume, let me, for a second, assume that A did have an inverse. Now, let's see where that gets us. My argument is going to be precise from here on. And at the end, I'm going to get to a contradiction, something that doesn't make sense. And then we'll know something was wrong because my argument was all watertight. We know that the original assumption, the assumption that I made right at the beginning when I said that A had an inverse must be wrong and A could not have had an inverse. If A has an inverse, so what? Then that means B times A is the identity, the 2 by 2 identity. Okay. Well, then I will say that if BA is identity, then BA times D is the same as identity times D. Well, BA and identity are the same. So if you multiply them by D, you should get the same thing. But identity times D, well, that's D. And BA times D, well, that's the same as B times AD because matrix multiplication is associative. That was the subject of a previous video. Matrix multiplication is not commutative. You can't move things over from each other, but it is associative. You can put the parentheses anywhere you want. So instead of BA times D, you can write B times AD, and AD was the 0 matrix, and B times the 0 matrix is the 0 matrix. So this BA equals identity then implies that the matrix D is the zero matrix. But evidently, D is not the zero matrix. In fact, it has no zeros in it. So this is a contradiction, and it proves that our original assumption that A had an inverse was wrong. So B does not have an inverse. So even though I haven't told you how to find inverses, I've given you an example of a matrix does not have an inverse and proof to you that it doesn't have an inverse. It's not that just that I can't find an inverse. No one can. And I also gave you an example of a matrix with its inverse. And if I give you the inverse, checking it is just a matter of multiplying the two matrices together. In fact, for 2 by 2 matrices, you can figure out what inverses are pretty straightforwardly. So if you start with a matrix A, B, C, D, just sort of a generic 2 by 2 matrix where these are real numbers, actually they don't have to be real numbers. They could be elements of any field. We have talked about fields in previous lectures, but again, if this is your first time to linear algebra, whenever you hear the word field, just think real numbers. So let's for now think real numbers and ask what's the inverse of A. And so we don't know what the inverse of A is, and we'll say, okay, what about, let's just say that it's something like X, Y, Z, and W. X, Y, Z, and W are yet to be determined numbers that I want to have to work for A. Well, then I write A times A inverse is identity, and that will give me 4 equations and 4 unknowns. A times A inverse, you multiply them, it will have 4 entries. Identity has 4 entries, and each of those will have to be equal to the corresponding one, and therefore you get 4 equations and 4 unknowns. You solve them for X, Y, Z, and W, and you will get what A inverse is. In fact, what you will get is that if A is A, B, C, D, you get that A inverse is 1 over AD minus BC times this other matrix, which is first column is D minus C, and the second column is minus BA. In fact, this matrix is easy to remember. All we did was switch the place of A and D, and then B and C kept their places but became negative. And then we're dividing by this AD minus BC. Well, does this say that every 2 by 2 matrix is invertible? No, it will be invertible as long as I don't have a 0 in the denominator. So as long as AD minus BC is non-zero. In fact, that's the constraint. That's the thing that will make a matrix not invertible, is to look at AD minus BC. If it's 0, then it will not be invertible. Otherwise, it will be. So for 2 by 2 matrices, this matrix is invertible if and only if AD minus BC is not 0. And that AD minus BC is called the determinant of this matrix. You might have seen the determinant of 2 by 2 matrices. Later, we will talk about determinants of 10 by 10 matrices and related to invertibility as well. And in fact, the same fact will work there. The determinant is always non-zero if and only if the matrix is invertible. By the way, this matrix here, so A inverse is 1 over the determinant times this other matrix. This matrix is called the adjoint, and that has a definition, and we'll get to that when we talk about determinants. And this rule will also work for more general matrices, although it's not a very good computational rule. It's sort of useful in terms of some theoretical aspects. The rule being A inverse is 1 over the determinant of A times the adjoint of A, whatever those things are. So don't worry about them. But anyway, for 2 by 2 matrices, it's sort of relatively straightforward to find the inverse. For larger ones, there's a method, as I suggested, but that will be the subject of later videos. For now, what I want to do, first of all, I want to justify saying the inverse. When I say the inverse of a matrix, I'm implicitly assuming that there's only one inverse. I'm not saying a inverse of or an inverse of the matrix A, or I'm saying the inverse of A. And so that's what I want to prove, that that's justified. So if the n by n matrix is invertible, then that inverse is unique. So let's prove that. How am I going to prove that? For every proof, you have to have a strategy. So what I'm going to do is that I'm going to assume that 2 matrices walk through the door, and they said that they both claimed to be the inverse of A. Now, what do I want to do? You might think I'm doing a proof by contradiction. I would have been doing a proof by contradiction if I also assumed that C and D are 2 different matrices that walk through the door and claimed to be the inverse of A. If they were different and said that, then I should be getting a contradiction. I'm actually not doing a proof by contradiction because I'm not assuming C and D are different. Instead, what I want to show is that, in fact, they are the same. So I'm saying that any 2 matrices that walk through the door and claim to be the inverses of A are actually the same matrix. That proves that there's only one inverse to A. Okay, by the way, we are assuming that A is square and it's invertible. Okay, so Now, C and D are both inverses of A. So what? Well, C being an inverse of A, that means that C times A is identity. And D being an inverse of A means A times D is identity. Okay, so what? Well, then we also know matrix multiplication. I alluded to this before. It's a subject of a previous video. Matrix multiplication is associative. It's surprising how many times we use this associative property. So if I want to find CAD, I could do CA times D or C times AD, and both will give me the same thing. But so this is again because matrix multiplication is associative. But now if I look at CA, well, that's identity. And if I look at AD, that's identity as well. And on the left-hand side, I have identity times D. Identity times any matrix is just that matrix. Identity times D is going to be D. And C times identity is going to be C. And so that says C is equal to D. Actually, it says D equals to C. Because this side became D and that side becomes C. So D equals C, which is the same as C equals D. And so I just proved to you that if you start with two matrices that are claiming to be the inverses of A, they must be the same matrix. And therefore, there's just only one matrix. I didn't prove to you that A has an inverse. I assumed it does, but then showed you that in such a case, there's only one matrix. Okay, so now the final thing that I want to show you is that if you like to have invertible matrices, and we like to have invertible matrices, if you have some of them, multiply them and you get new ones. You can create new ones from old ones. So if A is an invertible n by n matrix and B is an invertible n by n matrix, both of them are square of the same size, then the claim is that AB is also invertible. Not only that, I will actually tell you what the inverse is. The inverse is going to be what you think. AB inverse, that means the inverse of AB. AB is the product of AB, and I'm telling you that AB inverse is what you think. What it is B inverse times A inverse, which is different than A inverse times B inverse, because matrix multiplication is not associative. And this is known as one of the socks and shoes theorems, because the way to think about this is that if you put on your socks and shoes, and then you want to take them off, you have to take off your shoes first, then the socks. You can't do it the other way around. With operations that are not commutative, like for example, putting on your socks and shoes, it makes a big difference if you put on your socks, then shoes, or if you put your shoes on, then you want to put on your socks. Then if you want to undo them, then you have to reverse the order. So this is an example of a socks and shoes theorem. There are others. Okay, so how am I going to prove that? Well, I want to prove to you that AB is invertible without knowing what A and B is. And that seems like a tall order. Like, how am I going to prove that it has an inverse if I don't know what it is? But the key is that actually that second part is helping me out. It's telling me what the inverse is. It's claiming that the inverse of AB is B inverse A inverse. So the question is that, is B inverse A inverse lying, or is it really the inverse of AB? And if a matrix, so this matrix B inverse A inverse has walked to the door and is claiming, I am the inverse of AB. How do you check that? The proof of the pudding is in the eating. Just multiply them, see if you get the identity or not. Multiply it by AB and to see if you get identity or not. So if you take B inverse A inverse, this claimant, and times AB, do I get the identity or not? Again, we use associativity. We say, well, B inverse A inverse times AB is the same as B inverse times A inverse A times B. But then the advantage of that is that A inverse A is identity, and B, and so I get B inverse identity B, and that's B inverse B, and B inverse B is identity. So if I multiply B inverse A inverse times AB, I do get identity. Now, as I said at the beginning, I don't actually need to show them the other side, but I haven't proved that. So I do need to show also that AB times B inverse A inverse identity, but that argument is exactly the same as the one before. You just switch the parentheses and you get B inverse in the middle. That's identity. A times identity is A. And so you get A times A inverse and you get identity. And therefore, the product of two invertible matrices is invertible. And not only that, we know how, if we know the inverses of the individual matrices, we also know how to find the inverse of their product. This is the end of this lecture. If you like to be subjected to videos like this, then please like and subscribe. Otherwise, don't. And I will see you at the next linear algebra lecture, or possibly at a combinatorics lecture, or an abstract algebra lecture, or some other kind of a lecture. See you later.